So let's start by solving this simple quiz. A 1,000 kilogram car goes from 0 to 100 kilometers per hour in 6 seconds. So what's my initial kinetic energy? Initial kinetic energy is 0. Why? Initial velocity is 0. My final kinetic energy will be 1/2 mv final square. How much work does the engine do? Well, the change in my kinetic energy must be the work done by the engine on the car, right? So this is equal to 1/2 mvf square. How about the average power? What was our definition of power? Power was work done per unit time. So the average power will be work done by delta t, so which is 6 seconds. So that's going to be the answer. Are there any of you who are interested in cars? You know, people who follow what cars do. So how is this acceleration in 6 seconds, 0 to 100? It's not too bad, right? That's your average car out there, right? If you're, it's like certainly. So it's not going to break any records. So let's actually calculate this number. Let's see. So what's a typical horsepower of a car which would go to from 0 to 100 kilometers in 6 seconds? You know? Sorry? 80 to 200. So I mean, if you're a typical car enthusiast, they'll say, hey, that's a typical, you know, your mother, father's car that drives you around. That's pretty much around, at most, 100 horsepower. So that's my expectation. But let's see what the numbers actually tell me. So first of all, I need to calculate this work. But Vf is given as 100 kilometers per hour. What do I need to do? I need to convert this to SI units. In SI units, that's going to be 10 to the 5 meters per 60 times 60 seconds. Let me quickly calculate that number. Instead of a calculator, I'll use a glorified calculator here. Okay. So that's a nice program which I assume all of you will get more familiar with during your study at Bilkent. But here's what I really want to do. I would like to just divide 10 to the 5 by 60 times 60. And this is apparently 277.8. Am I doing something wrong here? Yes. Why? Let's check it again. It's 10 to the power 4. Why? I think it's 10 to the power 5, isn't it? Yes. Let's be more careful. Maybe I'm doing so 100 kilometers per hour is, yes, I should write 1 e to 5, right? Thank you. Divided by 60. 60 times 60 is 27.7, which is a much more reasonable. Let's make this 8 meters per second. So work should be 1/2. My mass is 1,000 kilograms, and then I have 27.8 square. Let me do that also. 1 e to 3 times 27.8 square divided by 2 is, that is 3.86 10 to 5. 3.86 10 to 5 joules, not watts, right? And for average power, I need to divide this by delta t. This was seconds, 6 seconds. 10 to 5 divided by 6. So this is 6.4 10 to 4. 6.4 10 to 4 watts. But I was asked to express this in horsepower. (6.4 10 to 4) divided by, the conversion factor is 745.7. Let's do that too. .4 horsepower. So the numbers come out to be okay. But let me tell you something interesting. When I what should be the power of an engine so that you can keep 100 kilometers per hour constant throughout the range? Would you do any work on your car when you're actually, when your engine is, or when your speed is constant? Okay, so if I had a frictionless engine, frictionless road, and no air friction, obviously my engine did not have to do any work. But on a real road, you spend a lot of, and your engine is actually supplying the energy lost to friction. It turns out, especially at higher velocities, most of the energy, most of the gasoline you burn actually goes to countering the force of friction on your car. So much so that that friction is mostly not related to your tires. It's mostly air friction. That's why having a, that's why sports cars or racing cars have these aerodynamic designs which basically just reduce the force of friction, air friction, drag friction on your car. Okay? So basically what we are doing when we are driving around is we are heating the air. We are just, burning some gasoline, turning it into not even kinetic energy. We are just basically countering air friction. Any questions? Who found a similar number for horsepower? Okay, good. Now I'm feeling more confident. It's my solution. Good. Now let's see. Let me solve one more example. Let's say that I have some circular or some rounded track which has no friction, and here I have friction coefficient mu k. So what I'll do is I'll drop a mass m from the top of the track, which has a height h. Okay. So what will this mass do? It will just run down the track, and then because friction is acting on it, it will actually travel some distance and come to a stop. Right. What I would like to find out is what's the length that this object is going to travel. Okay? And second question is, so the first question is length traveled on the track with friction. The second question is how long does the whole motion take? Okay? Let's solve the first part. Is energy conserved in this problem? No. Why not? Because of friction, and friction is a non-conservative force. But still, I can use the work-energy theorem, right? I will say, at the end of the day, the change in my energy must be equal to the work done by friction. Okay? So, can you tell me what's the final energy of my mass? What's the kinetic energy, final kinetic energy? It's 0, right? It's stopping. What's the final potential energy? Well, I didn't tell you which level to use as your reference level, but let's be reasonable and use this as our reference level. In that case, my final energy will be just 0. Can you tell me what my initial energy will be? This is left from rest, so initial kinetic energy is 0. So initially I only have gravitational potential energy, which will give me m times g times h. So what is delta E? E final minus E initial. It's equal to 0 minus mgh, so it's minus mgh. And that must equal work done by friction. When this mass is moving to the right, which way is the friction acting on it? Friction is opposing the velocity. So if my velocity is to the right, friction is to the left. And is the friction force constant throughout? Yes, it is. This is kinetic friction. Can you tell me what's the magnitude of the friction force? Mu kinetic times the normal force, which is going to be mg. Excellent. So if friction is mg times mu kinetic, what's the work done by friction? It's going to be F dot d if it's just a constant force. But what's my displacement vector? It's only displacement during which friction force acts, right? So it's only the displacement on the frictionful part of the track, right? So my displacement vector is a vector which goes from 0 to L here. So, but the displacement vector and friction force are in opposite directions. So this is going to give me minus mu k mg times L. Let's equate these two. Delta E is equal to work done by friction minus mgh is equal to minus mu k mgl. G's cancel, minuses cancel. So apparently L is just h divided by mu k. Did I reach my goal? Yes. How about units? What's the unit of mu k? It doesn't have units, and h and L are both meters. But this is fantastic. It tells me that the length you travel on this track with friction only depends on mu k and how high you left the object from. Right? It doesn't even depend on gravitational pull. Okay? Even if you did the same experiment on Mars, you'll get this same result. Does it make sense? What should this length be if there is no friction? If mu k is 0, this length would be infinite, right? So it does check. When I said mu k equals to 0, this length goes to infinity. So first part I have solved. How can I solve the second part? Any ideas? Can I use energy conservation? Who says no? Ali, tell me why. Why can I not use energy conservation? Yes. So whenever I use work energy theorem, I'm throwing dynamics out of the window. I'm not writing equations which depend on time. Sorry? Okay, so what happens is that energy is a conserved quantity. What does conserved mean? It means derivative with respect to time is equal to 0. So basically, what does that mean? It means we're looking at things which do not change with time. That's why we cannot actually get any time dependence from the work energy theorem. Another comment over there? No? Okay. So here's the thing. Can I really answer this? How does the whole motion take? The last part maybe I can find out. Right here, I can actually tell you how long this motion takes. But to be able to actually answer this question, I need to tell you what kind of track this is. Is it really a circle, or is it a parabola, right? Or maybe it does have a bump on the way. For all these three different tracks, the first part of the question would be the same. My final length traveled on the part with friction would not change. However, the time it takes for this object to traverse that rail would actually be different. And right now, with the level of mathematics you know, it will not be possible for you to calculate that time. Okay, you need to learn a little bit more. You need to learn differential equations, how to solve differential equations to be able to actually solve for that time, depending on the track. And here's a really nice question. Which shape do you think gives the minimum time for this track? So you know this was a problem. Yes, so this is a question that you're going to tackle in your analytical mechanics course next year, hopefully. This is for physicists. Chemists are not going to learn it. So
that's what used as a time precise clock.
So okay, you'll learn that it's a shape called just a moment. It's a shape which is actually very easy to define, but for a while that was a question with a money attached to it. So someone asked that question and said, whoever solves this, I'm going to grant them some money. So for the almost half of the physicists, half of the incoming physics classes in this section. That's why I'm mentioning all these interesting problems that you're going to see over the next years, okay? It's called the minimum time problem or Brachistochrone problem. Okay. Good. Now, let's solve one more example. Again, with these frictionless tracks. That's again a very standard question. And it happens that my son actually has a very nice toy model of that. Okay, you can buy it as a nice toy. So we have a almost frictionless track that's looping around itself. Okay. So basically, you want the car to go through this track, which has a radius r. Okay? So the question is the following. If my gravity acceleration is g, mass of the car is m, what should be the minimum speed so that this car can pass through this loop without falling down? Okay. Obviously, if you send it with very small velocity, the car will just go to the slope. Its energy will run out. It will all be converted into potential energy. Then it will come back. Okay. If you increase your velocity a little bit higher, it will actually go more than 90 degrees on the track. Then it will fall. Okay. So we want the minimum velocity so that it can actually pass through the loop without falling down. Okay? Good. So what's the point with the smallest speed throughout this motion? At which point would I have the smallest speed? At the topmost point. So what I must guarantee is, even at the topmost point, my car does not fall down. Okay? So let's do that. Let's look at the top point. Yeah. So let me redraw this. Oh, terrible. So at the top point, if my initial velocity here is vi, what's my velocity at the top point? Let's try to calculate that. Throughout this motion, are there any non-conservative forces acting on the system? No, there is no friction. We ignore air friction. So this whole motion should be conservative, which means my initial energy and my final energy should be equal to each other. What's my initial energy if I take the ground level to be my reference level? There is no gravitational potential energy. My initial energy is just 1/2 m vi square. How about my final energy? Well, my kinetic energy will now be 1/2 m v final square. But now I actually have mg times 2r of potential energy. If my initial energy is equal to my final energy, 1/2 m vi square is 1/2 m v final square plus 2 m g r. M's cancel. I should say v final is square root of 4g r minus v initial square. Now, do I actually check if, is there a problem? Tell me. Good. Someone is actually following what I'm doing here. Minus 4GR. Thank you. Now, how can I check if this speed is enough to keep me on track? What would happen? How does this, let's say that my speed is not enough to keep me on track. How can I check for that condition? What happens when I am leaving the track? Why do I follow a track? I follow the track because it actually gives me a normal force to change the direction of my velocity, right? So what would the normal force be if I am leaving the track and falling? The normal force would be 0, right? If this was not just a track, but it was basically it was not a car on a track, but a bead on a wire. Okay, if I had a bead on a wire, it would actually go through. It would never fall off, because it can have not only positive normal force, it can also have negative normal force. Okay, now, so let's calculate the normal force the track applies to the car at the top. Okay, so what's the normal force? If my speed is v top, how do we calculate forces? We draw free body diagram. So let's draw a free body diagram for my car. What forces do I have? I said normal force will be down. I will also have mg down. Do I have any other forces? No. These are the two. But does this car actually have an acceleration? Yes, it's going through a circle. Which way is the acceleration pointing? It's towards the center, which happens to be basically down. What's the value of this acceleration? It should be v squared over r. So this is my acceleration, which is vt squared over r. So ma must be n plus mg. So my normal force must be ma minus mg m vt squared over r minus mg. So, question. Okay, that's very good. It is, in effect, going down. But the track is curving faster than it's falling down. In that case, you would actually stay on the track. If the track is not curving as fast as this guy is falling down, then you would get off the track. Okay? That's why normal force tells you the normal force is the result of a constraint on moving that track. If the normal force becomes 0, it means that you are leaving the track. Okay? So let's set this normal force to 0. So normal force is 0. So this is leaving the track at the top. It's going to be m vt squared over r minus mg. M's cancel. So v top in that case would be square root of rg. So essentially, not to leave the track, vt must be larger than square root of rg. Did we actually express Vt in terms of my initial velocity? Yes, we did. I somehow called it not Vt but Vf. Should be T. So I'm just writing this down. Vt, which is square root of V initial square minus 4rg, right? Should be larger than square root of rg. I can take the square of both sides. Vi square minus 4rg must be larger than rg. So my initial velocity must be larger than square root of 5 times rg. If I send this toy car with a velocity larger than this value, it will actually pass through. If I send it with a smaller velocity, it will actually fall off the track or maybe come back. Okay? Let's quickly check. Did I reach my goal? Yes, I did. R and G were given. Initial velocity was asked. How about units? R has units of meter. G has units of meter per second square. If I take the square root, this is meter per second. That's what I need. How about the limits? If G is equal to 0, if I'm at 0 gravity, I would pass through this track no matter what happens. That actually checks. And if R is large, if you have a loop with a large radius, you should need more velocity to pass through this loop. So that also checks. So I think we actually found the correct answer, at least dimensionally. Question?
What if V initial is equal to?
What happens? So should I actually put an equality sign here? Okay, that's a good question. And the answer is, at that point, you momentarily lose contact with the track. Okay, and then you'll actually make a small collision with the track a moment. Okay. So I did not specify how this collision takes place, so it's maybe not a good idea to put equal sign there. Right? That's the critical point. That depends on the elastic properties of the track. All right? What I mean, I wouldn't. It would not be exactly wrong to put that sign there. Any other questions? Let's take a 10-minute break, and when you come back, we'll talk about it.